So, in today's lesson, you're going to get a bunch of everyday situations, and we're going to together figure out mathematically how we can model them. And we're just going to go step by step through it, and hopefully, the exercise it's something that you'll think that there's a connection to math to the real world. That's the hope. All right, let's look at the first situation. It's about a plumber, and a plumber charges a fixed fee for coming to your house, then charges a fixed amount per hour on top of this. So, some words I'm focused in on is fixed, and the other word is fixed. So, some things I'm thinking about is this a model where it's going to grow over time? So, I need to know if it's increasing or decreasing. So, the longer this plumber, notice it's a female plumber, awesome, maybe, will it take, the longer she does the job, the more it's going to cost. So over time, it's going to increase. That's the first thing I look at. And how does it increase? Is it increasing at the same rate, or does it increase faster over time, and so on? So this word fixed means it's going to increase, and it's going to be a constant increase. So what we're looking for is a line that increases to model this situation. So next, what I want us to do is I want us to look at the equations or the graphs on page, it's either 3 or 4 of what I gave you here. Let me look here. 1, 2, 3. Starting here. And think which of these graphs it could be. So the first graph, does this model the plumbing situation? It's decreasing. No. Does this one model the plumbing situation? It's a line. It's increasing. This has potential. G3 is completely empty, and so is 4. So that's something you're going to have to graph in terms of it. G5, is that a parabolic situation where you have a maximum and then the price decreases? No. This is increasing, but it's curved, so it's not a constant increase. This one also has potential because it's a line and increasing, so we got 2 that are potentials. No. Decreasing, decreasing. The price goes up and down over time? No. And then increasing, but increasing with the curve. So there's only really 2 that could do it. So if I look at G7, and I'm going to put G2 right beside it, if I look at those beside each other, which one could be the situation? So again, a plumber starts with a fixed cost, and then it increases over time. So I want you to know that the original price here would actually be 0, and then the rate goes from there. This situation here, we're not starting at 0, we're starting at a number and then increasing from there. So I want you to notice of all the graphs that could model that situation of a plumber, the one that matches it is this one, G2. So the next thing we're going to look at is the third part. And the third part is which of these equations, and they're all on this one sheet, which of these equations would match this graph. So what am I looking for? So I'm looking for an increasing, so a positive slope line that starts at a positive number. So A1, what's wrong with A1 is that it is a positive slope line, but it starts at -10. No, oh, that's a positive slope, but it starts at 0. 3, maybe, positive slope starts at 60. Here, a negative slope, no, not linear, not linear. Any other lines here? The rest are not linear at all. So when I look at them, the only one that could match the model of the plumbing situation is right here at A3. So we're going to put this together. In fact, I am going to get a separate piece of paper out. Let me do that right now. And let's start. So this is everyday situations. Uno. Here we go. So first we looked at the plumber. So what I want to know is the equation and the graph that goes with it. So we're going to work back. We're going to start with the graph, that the equation I said that would match with it. And the equation that matches with it is A3, which is y equals 40x plus 60. The graph of that would only be a graph in the first quadrant. And in this situation, x is the number of hours. The y is the total cost. And we're matching this plumber situation. So if I was going to graph this, I would understand that it's going to start at 60. So I'm going to count by 20s. So 20, 40, 60, 80, 100, 140, 180. See if that gives us a shot, at least at graphing it. So we know originally it's going to cost $60. And then from there, if I look at the first hour, we're going to increase by $40. So the first hour, it's now going to cost $100. The second hour, we're increasing by $40. So now it's at $140. At 3 hours, we're now at $180. And then you have your line that describes that situation. So you have the equation, you have the graph that goes with that real world situation. And now, is there a question? And then the question that goes with the picture is, how much does the plumber charge for a 3-hour job? So then the last step is that we're going to plug in 3. We already solved it, but it's 180 off the graph. So the plumber charges $180 for a 3-hour job. Done. B. Let's look at that situation. So in B, we have someone bicycling. A cyclist travels along a direct route from town A to town B. The distance of the cyclist from town A in miles, and the distance of the cyclist from town B in miles. And then it says, how far apart are the towns? So he's going from town A to town B. Doesn't quite tell us a lot about the rate that the bicyclist is going at, but we say the distance that they are from town A to town B, which is one that could understand the distance from A. And X is the distance from town A, and B is the y-axis, the distance from town B. So which one could be it, which one may not in terms of what we're looking at. So let's look at the different graphs again and try to get a sense of it. So we've already looked at G2, so that's not it. So now let's look at some other ones. Now, for G1, we have an asymptote and an asymptote, so we're not looking at that one for this situation. G3 and G4 are empty, so it might be those. We might have to create our own model. G5 is a parabola. Would that model the situation? Think through that. G6, we have a increasing function that kind of looks like a square root function. G7, we have this situation, which is a line. G8, we have that parabola. G9, we have a decreasing curve going down. G10, I want to really focus on this one. So on G10, we have a linear situation. Now, in this model situation, if he starts at in town A and is going to town B, then on the x-axis, how far, and if this is 0, if he starts here, then the distance the bicyclist is from the town he's starting at would be 0. But as the bike, I'm going to try to travel, oh, there's my bike. As the bike travels to town B, what's going to happen here is that on the y-axis, so this is town B, this is town A, the distance from, that it's actually going to get closer and closer and closer, where when we actually hit the axes again here, the y value is 0, which means he's at town B, and the x value is whatever that x value is down there in terms of being away. So he starts at town A, so he's there, and then as he's traveling, he gets further and further away from town A, but at the same time, he's getting closer and closer to town B. So this models that situation of a bicyclist starting at town A, it's 0, they're at, and then as they go along, the x value increases, but the y value decreases until it's 0 and he reaches town B. So the distance to town B now is 0 at the very end of the journey. So we have a model. Now we need an equation that looks like this. What am I looking for in an equation here? It's a line. What do we know about the line? We know the y-intercept is positive, and we know it's a negative slope. So see if we can find that. So it can't be a positive slope, positive slope, positive slope. Let's look at this one, negative x plus 100. Do we have a negative slope, and do we have a positive y-intercept? It matches. The rest are not linear at all, so they can't match it. So let's go back to our paper. For this one, it's a cyclist. And for the cyclist, we said the equation that's going to model it, we just found it, is negative x plus 100. We're going to graph it. So already we know the distance between the towns is 100. So when he starts at town A, we'll count by 20s, 20, 40, 20, 40, 60, 80, 100. I can so do that. There it is. So counting by 20s, I'm going to do the same thing here, 20, 40, 60, 80, 100. So we know here the y-intercept's 100, and then when x, what's the x-intercept? When you plug in 100 for x, the answer is also 0. So we can just connect these two exactly how you see it. And we have the x and the y axes, where x is the distance from town A, and y is the distance from town B. Now there's a question. And for part B, the question that is used, here again, go back. Oh, how far apart are the towns? That's the question. Well, we kind of answered that already. How far apart are the towns? And the answer is the towns are 100 miles apart. So when you're at town A, it's 100. When you're at town B, it's 100. So you can see that they are 100 miles apart. All right, part C. Let's look at that. So a movie subscription, you get 2 movies free, but then you get charged at a fixed rate per movie after that. And the number of movies seen is X, and Y is the total money spent in dollars. And it says, what is the fixed rate per movie? So I like the word fixed. So I like the word fixed because it gives me a sense it's linear. This is increasing, but I want you to get a sense that at the very beginning, it's not going to cost you anything for the first 2 movies. So I want to get at which would model a linear situation, increasing, but at the beginning, you're not spending any money until the 3rd movie. So let's look at the graphs again, and which one could model that situation. Get the graphs back here again. So I don't see it, not the curve. We've already used G2, not going to model it anyways. We have some curves here, not linear. G7 has potential, right? But the only issue with this is it's starting at 0, and at one movie it's going to cost you. So this line is not modeling our situation. So at the first 2 movies, it should be no money at all. And then by the 3rd movie, then it's going to cost something, and it goes up from there. G8 curved, G9 curved, so it's not a fixed rate. Here we already used G10, it's decreasing. We have a trig wave here, and that's not going to be going up and down for the cost. And another curve that isn't a fixed rate. So I actually don't see the graph. So it's probably one of the empty graphs here, 3 and 4, that we have to draw ourselves. So we have to go to the equation then to see it. So for this situation, we're going to go to the equation. And again, what am I looking for? I'm looking for something that's increasing. So I already used A3. A4 is not increasing. These are both increasing, but which one's going to model it where the first 2 movies are free? Well, for this one, you don't see it, but it's going to start at 0. For this one, it starts at -10, which doesn't make sense. How can something cost -10? Well, we're going to draw it with that domain restriction so that you won't have a negative value underneath. So this is what I mean. So for part C, what was the name of the situation? So for part C, this is the movie subscription. And what I want you to show, the equation, which we're going to graph, is 5x subtract 10. Now, when we graph this, again, we're only going to graph it in the first quadrant for a real situation. No negative values here. So I'm not going to start at -10. So I realize that I need to start with positive values. So if I plug in 1, or if I plug in 2, well, if I plug in 2, 5 times 2 is 10, and 10 take away 10 is 0. So I'm going to start there. And then when I plug in 3, now it's certainly going to cost $5 more per movie. So when I plug in 3, you can have 5, and now here we are. It's going to cost $5. And then the next one, the 4th movie is going to cost $10. The 5th movie is going to cost, the 3rd movie is going to cost 5. The 4th movie is going to cost $5 increasing every time. The next one's going to be 15, right? Now, a couple things I want you to notice here for this situation. I want you to notice I'm not connecting these points. That's because you can't see 2.5 movies, or 3 1/4 movies, or 4 1/5 movies. You can only see whole numbers. So to model the situation, it can only be points, but not connected points to make it continuous, because only the whole numbers is what we're interested in. So for 5x subtract 10, notice I didn't start at -10. Notice that at 1, we could also put this answer down here to be 0. And at 0, obviously, the answer is 0. So you have the values here, but this then is modeled by this equation where it's increasing. So can you see 0 doesn't cost anything, 1 doesn't cost anything, 2 doesn't cost anything, but now 3, 4, 5, it starts now increasing at $5 a piece. So what does the x-axis represent is the number of movies. What does the y-axis represent is the cost. So now we have a graph. We're not connecting them because you can't have values in between them. We have a model to go with, and then the question is, what is the fixed rate per movie? So what is the fixed rate per movie once you get the first 2 ones free? And you can see we're increasing by how much? So the fixed rate is another word for slope. So the fixed rate per movie is $5 and starts after watching the second movie. So after the second movie is when it starts. All right, so there's part C. All right, I'm going to do another movie, or video movie, we're talking movies, on the next modeling. We're going to look at some more. All right, Mr. G Math, over and out.